All right.
Are we given the formulas for the exam?
I don't know if I'm going to give you a formula sheet, but you have an open book exam. So my suggestion is go ahead and build yourself a formula sheet as you're going through everything. And really, like, if you just take the main laws and the core principles, and you know how to like work through them like we were to get to the equations with like I squared R is equal to V or whatever, you'll be solid. Or you can just take a picture of the power wheel and pop it on a page, and you got like 10, 16 formulas there.
Are we having an exam for the lab as well, or
Final exam for the lab, no midterm.
no midterm?
No midterm for the lab.
Even for the lecture portion?
Lecture portion, there's going to be 2 midterms, and I'm going to make them both remote over the break, if I'm not mistaken, because we're going to end up being a week behind because of the week that we missed. So I'm just going to give you guys the extra time to do it at home. You open it up during reading week. You go in, you have an hour.
Okay, so it's just.
Yeah.
Got it. Thank you.
We'll use the trust system, but you know, you're not doing yourself any favors by not using it as a real test. If you were to like, you know, copy off someone that's right next to you, chances are on the final exam, you're not going to have that friend next to you, and instead of losing 10% or 5% learning your lesson and doubling down on your efforts, you'll end up losing your 40%. And if you're not doing better than 50 in the course overall by then, that's like instant fail. So I wouldn't risk it. You'll probably get 45 minutes to build and troubleshoot. Okay. What's your question?
Is there two?
Midterms? Yeah, there's 2 theoretical midterms.
And they're all.
I'm going to make them both during reading week for you guys. Okay, let's kind of go through this pretty quick, Lucas.
Question about the lab exam.
Yeah.
How advanced or sort of like complex is it like the final lab?
It's going to be more complicated than Lab 7.
It doesn't work with
Not terribly more complicated, but a little bit more complicated. And by the time you do that, you don't have to do any design work. By the time we get to the final exam, you're expected to be able to build pretty much anything, which is why you start building your own circuits and designing them, because then you run into logic issues, and you don't have to worry about logic issues on the final. Okay, guys, let's do this. Okay, so guys, we're going to talk about voltage drop, voltage potential. Voltage potential is anything from that voltage. So like, let's say there's point A, B, C, and D. Let's say we want to know the voltage potential of B. It's from B all the way to 0 volts, wherever 0 volts is. If we wanted to know the voltage drop, we'd have to define the second place it's going through. So we either have to talk about R2, which is the resistor, or the voltage drop of BC. So voltage drop of R2 would be between B and C, and it's the same thing, right? So voltage drop, voltage potential is always relative to 0. Drop is how much does that component use up, okay? Same story here, it just shows you the different parts. I really advise taking a few minutes to open up this slide and just dig into it a little bit more thoroughly. And so if you wanted to know, let's say the voltage of R1 is over here. You could take the voltage at A and the voltage at B, take the difference between them, and you'll end up with the voltage drop at R1. Now, the reason that's really cool is because let's say all 3 of these resistors are the same amount of resistance, and we have a 24 volts, or let's just make it simple, a 30 volt source. Over here, there'll be 30 volts because we still are at the main voltage source line. It hasn't gone through anything yet, so there's been no voltage drop. After the first, so after this one, there's been 1 voltage drop, 2 voltage drop, 3 voltage drop. We know that they're all going to be the same, so each one of them is going to have a voltage drop of 10 volts. So at A, the voltage is going to be 30 volts. At B, the voltage will be 20 volts. At C, the voltage, at A, the voltage will be 30 volts. At B, the voltage will be 20 volts. At C, the voltage will be 10 volts. and at D, which doesn't exist, but you know where D is, it would be 0 volts, right? So if I took A minus B, it would be 30 minus 20 volts, which would be 10 volts. If I did B minus C, it'd be 20 minus 10, which would be 10 volts. If I did C, C is 10 volts minus 0 is going to be 10 volts. So all three of them use up 10, but that's where the drop comes into play. Now voltage is relative, that's kind of what we were just saying, so voltage potential is always going to be relative to 0 volts. Whenever you see these three lines here, it usually means ground. As we said, ground is really going to be talking about 0 volts when we're talking about DC, so these two are really connected. So when you see this going from here to here, it's really just saying from whatever this point is between R1 and R2 to wherever 0 volts is. Circuit ground can be used for any circuit, so you can just throw these symbols whenever you're working in a circuit like this, and it's always going to mean the same thing, right? Now measuring voltage with respects to ground. You guys know when I try to walk you guys through troubleshooting your circuits, I always say take your black probe and put anywhere on 0 volts, and take your red probe and try to trace back the steps until you get to the jump where you have voltage. And when you see you have your 24 volts on one side and 0 volts on the other side, whatever's in between those two is going to be your problem, right? So like, let's say we had 24 volts on one side of the switch, and on the other side we have 0 volts. You might realize that the switch is still open. So you close it and magically your circuit's working. Or you might find that when it's closed, there's 24 on one side and 0 on the other side. You know your switch has a problem. If on one side of wire you have 24 volts, the other side of the wire you have 0 volts, you know the wire's broken. So the point is, everything is always going to be relative to ground when you're talking about voltage potential, which is kind of something we covered already. And it's voltage drops can be measured across a resistor. And then voltage divider. So this is really the thing that we're here to talk about, because I think you guys have everything I said so far, kind of pretty good understanding of it. Someone correct me if I'm wrong. Now, you guys can kind of intuitively know that if you have the total resistance, forget about these numbers for a second. Let's say these were both 50 ohms and we have 100 or 10 volts. How much voltage is going to be on each of them? 5 and 5, because they have the same amount of resistance. Now we can start to look at each case. Let's say it's 50 and 100 ohms, like it has in this picture over here, and we can start to notice a trend that there's a very linear proportionality to the amount of resistance in a series circuit to the voltage of that versus the entire voltage and resistance. So there's a formula that I want to throw at you guys, just in case we don't get too far. Remember this formula above all. It is the easiest way to remember it. If you turn the voltage source over the total resistance into a ratio, so voltage source over resistance total as a ratio, it will be equal to the ratio between voltage of N over resistance N. Now, how can I prove this to you guys mathematically? Well, V is equal to IR, right?
Yep.
So I is equal to V over R, right? And we said I source is equal to I1 is equal to I2 is equal to IN. So if we're saying this is equal to that, we're really saying the current total is equal to current at N, which we know is true already, right? So if you remember this, you'll have a very easy time with voltage divider, okay? At least for series. It gets a little bit more complicated as we split things up, but for now, keep it simple and we'll build on it as we go. Okay, the thing that starts to get complicated, just to make it, like, to confuse you guys and hopefully deconfuse you guys later, is this voltage source and the resistance total. you have to kind of think what it is. Like, let's say there was a branch. We haven't talked about parallel yet. Let's leave it there. Just for this sake, when we're in a purely series circuit, voltage total and resistance total are the full total for the entire circuit. Once we start to have branches, you might want to think about it a little bit more in depth and break it down into smaller pieces. Okay, so over here, because we have this ratio that we talked about, if we want to move one over, we can say, okay, I have the voltage source and I want to know voltage of N. So you send this over to the other side, which will give us voltage N is equal to voltage source over voltage resistance total times, because we're multiplying both sides by the resistance of N, Rn. And that's your magical formula. Okay? So over here, we notice that this has 50 ohms, this has 100 ohms. If we were to use that exact formula, over here, we'll notice this comes out to 3.33 volts and this comes out to 6.67, aka 1/3 and 2/3 of the 10 volts. And this is 1 out of 50 over 50 is 1/3, and 100 over 150 is 2/3. So that's exactly the way that works. Does that make sense for you guys? Okay. And then we end up with this formula over here. And this is that fancy little this thing, whatever. This one's better, but this also works. And so, great. I think this is just an example. Why don't you guys try to do this really quickly? And I think we're probably just going to rush through the rest of it because we're already late for the lab. I'm sorry, I hate rushing you guys. Like some baseline of progression we have to make, but I need to explain it to you guys on some level at least. So go ahead, throw in the numbers. You're looking for the voltage of B. Resistance of 1 is 200 ohms. Resistance of 2 is 200 ohms. The voltage source is 40 volts. I think you guys could tell me exactly what VB is without doing any math. Everyone say it together. 20, exactly, great. So now it's just using the voltage divider formula to do that. So it does 200 ohms divided by 200 plus 200 ohms, which is the total resistance, times the 40 volts is going to give us the same 20. Great, and then here's another one. I'll let you, here the thing that we're trying to communicate is you can also say, okay, between B and D, I'm going to turn that into one total voltage or one total resistance. And you could add up 94 with 417 to create the resistance of R2 plus R3. And you could use the same voltage divider to figure out the segment over here. Does that make sense? So what they're doing is they're saying, okay, this 94 plus 417 ohms divided by all of the resistances added together times the 20 volts is going to give us our 5 volts for the section between B and D, which is the voltage of R2 and R3 together. Does that make a bit more sense now with that in front of you? Yeah, thumbs up? Okay, good. Other than that, we have something called a potentiometer. So the way a potentiometer works is there's a dial over here in the middle, and this connects into a filament in between. It says 1 and 2. So 1 and 2 have a set distance between them, and there's a filament that has a certain amount of resistance per amount of distance traveled on it, right? So if I go 1 millimeter, it's 50 ohms. If I go 3 millimeters, it's 150 ohms. If I go 10 millimeters, it's 500 ohms, right? So the more you go down it, the more distance it traveled through that filament, the more resistance it has, and it's accumulative. So when you connect from 1 to 3, that's when you're able to adjust the voltage. If you're connected from 1 to 2, it's always the same resistance. Sorry, resistance, not voltage. So how do we look at this? On a circuit, it's going to look like this, where you have 1 and 2, and then you have the dial of 3. And you could kind of, in a way, break it up into resistance 1 to 3 and resistance 3 to 2. So from 1 to 3 and then from 3 to 2. And those are going to change drastically, right? Like if you were to have these together, as you're moving that dial up and down, one's gonna get bigger while the other one gets smaller, but it's gonna be the same as the full distance between 1 and 2. Now, if you were to just have one or the other, that's where you can have different resistances or use the potentiometer as it's meant to be used. Where you turn it one way, the voltage goes up. You turn it the other way, the voltage goes down based on the resistance increasing and decreasing using Ohm's law. So this is giving us a bit of an example here. And you can see now we removed 2, so we just have A and B. And it's saying that potentiometer is set to 600 ohms. Go ahead and calculate the voltage between the 2 points. You guys know how to do that really quickly using the, what's it called?
Ohm's divider.
I think you have to use voltage divider. No, honestly, this is probably just the full 30 volts going through that. But you want, sorry, what's this asking? The dial is turned 1/3 of a turn. Okay, so if it's 1/3 and the entire potentiometer is 600 ohms, what's 1/3 of 600? 200. So it would be at 200 ohms over here. And then what's the voltage potential at point B? Well, B is going to be from here down to the rest, so it's 400 ohms. So this point between A and B is 200 ohms. The potential between B and 0 is the 400 ohms, is what that's trying to explain. And then you can see that over here it's saying 200 of the 600 times 30 volts, so it has a potential of 10 volts, right? And then the other side is, you know, from B to 0 is the 400 of the 600 times 30 volts, so that's 20 volt potential. Does that make sense? Cool. And that's it, okay? Great job. We'll see you guys down in the lab.